The Pluto-Neptune collision hypothesis, a cosmic enigma, explored introduction, the distant dwarf planet Pluto, once considered the ninth planet of our solar system, has long captivated astronomers and the public alike with its peculiar orbit and enigmatic nature. Recent speculative discussions by prominent astrophysicists, such as Michio Kaku and Neil deGrasse Tyson, have reignited interest in Pluto, suggesting the possibility of a catastrophic collision with Neptune. These claims, while sensational, raise critical questions about the stability of Pluto's orbit, the dynamics of our solar system, and the potential consequences of such an event. This article delves into the intricacies of Pluto's orbit, the gravitational interplay with Neptune, and the feasibility of a collision, while exploring the broader implications for our understanding of celestial mechanics. Pluto's peculiar orbit. Pluto's orbit is unlike that of any other major body in our solar system. Discovered in 1930 by Clyde Tombaugh, Pluto takes approximately 248 Earth years to complete a single orbit around the Sun. This extended orbital period means that, since its discovery, Pluto has yet to complete a full circuit. Its orbit is highly eccentric, with an eccentricity of about 0.25, meaning it follows an elongated, elliptical path rather than the nearly circular orbits of the 8 major planets. At its closest approach, perihelion, Pluto ventures as close as 29.7 astronomical units, AU, to the Sun, while at its farthest aphelion, it recedes about 49 Australian dollars and 30 cents. Adding to its uniqueness, Pluto's orbit is tilted at an angle of approximately 17 degrees relative to the ecliptic plane, the plane in which most planets orbit the Sun. This significant inclination, combined with its eccentricity, results in a trajectory that appears chaotic compared to the orderly paths of the inner planets. Most intriguingly, Pluto's orbit intersects Neptune's, which lies at an average distance of about 30 Australian dollars from the Sun. For roughly 20 years during each orbit, Pluto actually comes closer to the Sun than Neptune, a phenomenon that challenges intuitive expectations about planetary arrangements. This orbital overlap raises a fundamental question: why haven't Pluto and Neptune collided? The answer lies in the intricate gravitational dynamics that govern their paths, ensuring stability despite their apparent proximity. The gravitational dance. Pluto and Neptune's orbital resonance. The stability of Pluto's orbit is largely due to a phenomenon known as orbital resonance with Neptune. Specifically, Pluto and Neptune are locked in a 3:2 mean motion resonance, meaning that for every 3 orbits Neptune completes around the Sun, Pluto completes 2. This resonance ensures that when Pluto crosses Neptune's orbital path, the 2 bodies are positioned at a significant angular separation, typically around 90 degrees apart. This angular offset prevents close encounters, as Pluto is either well ahead or behind Neptune in their respective orbits. The resonance is further stabilized by the gravitational influences of the giant planets, Jupiter, Saturn, and Neptune itself. Jupiter, with its immense mass, plays a particularly significant role in maintaining the long-term stability of Pluto's orbit. Numerical simulations conducted in the late 1980s and early 1990s demonstrated that this resonance has kept Pluto's path stable for billions of years, preventing collisions or significant orbital disruptions. Another critical factor is the concept of asynchronous oscillation, which describes the relative motion of Pluto and Neptune as they orbit the Sun. When Pluto crosses Neptune's orbital plane, it is typically located far above or below Neptune's position due to an inclined orbit. This vertical separation, combined with the angular offset provided by the 3:2 resonance, adds an additional layer of protection against collisions. The VZK wobble, named after researchers who studied the 3-body problem involving Pluto, Neptune, and the Sun, further explains the stability of the system. The 3-body problem refers to the complex gravitational interactions between 3 celestial bodies, which are notoriously difficult to predict analytically. In Pluto's case, the VZK wobble describes subtle perturbations in its orbit caused by the combined gravitational pull of the Sun and Neptune. These perturbations, while small, contribute to the overall stability by ensuring that Pluto's path remains dynamically balanced over long timescales. The collision hypothesis. Fact or fiction? Recent claims by Michio Kaku and Neil deGrasse Tyson, as referenced in public discussions, suggest that Pluto's orbit could potentially shift, placing on a collision course with Neptune. These assertions have sparked widespread interest and concern, but how plausible is such a scenario? To evaluate this, we must consider the factors that could destabilize Pluto's orbit and the likelihood of such an event occurring. Orbital chaos and sensitivity to initial conditions. Pluto's orbit, while stable over billions of years, is sensitive to initial conditions, a hallmark of chaotic systems. The theory of orbital chaos suggests that small changes in a body's position, velocity, or external gravitational influences can lead to significant deviations in its trajectory over time. In the late 1980s, computer simulations revealed that even minor perturbations in Pluto's orbit could result in dramatic changes over centuries or millennia. However, these same simulations showed that the 3:2 resonance and the gravitational influence of Jupiter and other planets act as stabilizing forces, counteracting potential disruptions. For a collision to occur, a significant external force would need to alter Pluto's orbit in a way that disrupts its resonance with Neptune. Possible sources of such perturbations include close encounters with other bodies. A rogue asteroid, comet, or hypothetical trans-Neptunian object could theoretically perturb Pluto's orbit. However, the Kuiper belt, where Pluto resides, is sparsely populated, and the likelihood of such an encounter is extremely low. Gravitational influence of undiscovered planets. Speculation about a massive Planet 9 in the outer solar system has persisted for decades. If such a planet exists, its gravitational pull could potentially affect Pluto's orbit. However, no definitive evidence for Planet 9 has been found, and its influence on Pluto remains speculative. Long-term secular perturbations. Over millions or billions of years, subtle gravitational interactions with other planets could gradually alter Pluto's orbit. While these effects are real, they occur on timescales far longer than human civilization, making an imminent collision unlikely. The mechanics of a hypothetical collision. If Pluto were to collide with Neptune, the consequences would depend on the nature of the impact. Pluto, with a diameter of approximately 2,377 kilometers, is significantly smaller than Neptune, which has a diameter of about 49,244 kilometers. A direct collision would likely result in Pluto being absorbed or shattered by Neptune's massive atmosphere and gravitational field. The energy released in such an event would be immense, potentially altering Neptune's atmospheric composition or ejecting debris into the surrounding space. However, the immediate impact on Earth would be negligible. At a distance of over 30 Australian dollars, the collision would occur far from our planet, and the effects would be limited to observable changes. Angular and vertical separation. Pluto's inclined orbit and asynchronous oscillation ensure that it remains far from Neptune during orbital crossings. The vertical separation, due to the 17-degree tilt, and angular offset, due to resonance, provide multiple layers of protection. Lack of immediate perturbations. Current observations show no evidence of massive objects or events capable of disrupting Pluto's orbit in the near term. While long-term predictions are challenging due to the chaotic nature of orbits, no imminent threats have been identified. Historical stability. Pluto has completed countless orbits over the 4.5 billion-year history of the solar system without colliding with Neptune. This long-term stability suggests that the system is well equilibrated. Implications for Earth and the solar system. The sensational nature of the collision hypothesis has led to speculation about potential risks to Earth. However, as noted, a Pluto-Neptune collision would have minimal direct impact on our planet due to the vast distances involved. The primary consequences would be confined to the outer solar system, potentially affecting the dynamics of the Kuiper belt or Neptune's moons. Indirectly, such an event could provide valuable insights into celestial mechanics. A collision would offer a rare opportunity to study the effects of high-energy impacts in the outer solar system, shedding light on the processes that shape the early solar system. For example, debris from the collision could reveal information about Pluto's composition or Neptune's atmospheric dynamics. More broadly, the discussion highlights the importance of continued monitoring of the outer solar system. Advances in observational technology, such as the James Webb Space Telescope and future missions to the Kuiper belt, could provide new data on Pluto's orbit and its interactions with other bodies. These observations are crucial for refining our models and improving our ability to predict long-term orbital behavior. The role of computational modeling. Modern astrophysics relies heavily on computational models to simulate the complex dynamics of celestial bodies. In the case of Pluto, numerical simulations have been instrumental in understanding its orbit and predicting its future behavior. These models solve equations of motion for multiple bodies, accounting for their mutual gravitational interactions. By adjusting parameters such as position, velocity, and external perturbations, scientists can explore a range of possible outcomes. In the 1980s, pioneering simulations by researchers like Gerald Sussman and Jack Wisdom revealed the chaotic yet stable nature of Pluto's orbit. These models demonstrated that, while small changes in initial conditions could lead to significant deviations over time, the 3:2 resonance and other stabilizing mechanisms ensure long-term equilibrium. More recent simulations, leveraging increased computational power, have further refined our understanding of Pluto's dynamics. However, predicting the exact trajectory of Pluto over millions of years remains challenging due to the inherent unpredictability of chaotic systems. Even the most sophisticated models rely on precise initial conditions, and small errors in measurements can lead to significant uncertainties in long-term predictions. This limitation underscores the need for ongoing observations and data collection. The broader context, chaos and order in the solar system. Pluto's orbit serves as a microcosm of the delicate balance between chaos and order in the solar system. The concept of orbital chaos, rooted in the sensitivity of orbits to initial conditions, is a fundamental principle of celestial mechanics. Systems like Pluto's highlight how seemingly erratic behavior can coexist with long-term stability, thanks to gravitational resonances and other stabilizing mechanisms. The interplay between Pluto, Neptune, and the giant planets also illustrates the interconnected nature of the solar system. Each body's position and motion influence the others, creating a complex web of gravitational interactions. Jupiter's massive presence, for instance, not only stabilizes Pluto's orbit, but also shapes the paths of asteroids and comets in the inner solar system. This interconnectedness underscores the importance of studying the solar system as a holistic system rather than a collection of isolated bodies. Public perception and scientific communication. The claims by Kaku and Tyson, while speculative, highlight the challenges of communicating complex scientific concepts to the public. Sensational headlines about cosmic collisions can capture attention, but may also sow confusion or fear if not accompanied by context. In this case, the likelihood of a Pluto-Neptune collision is extremely low, and the claims appear to be more speculative than evidence-based. Astrophysicists play a critical role in bridging the gap between scientific research and public understanding. By presenting the nuances of orbital dynamics in an accessible way, they can foster appreciation for the complexity of the cosmos while dispelling unwarranted concerns. For example, explaining the stabilizing effects of orbital resonance and the VZK wobble can help demystify Pluto's orbit and reassure the public that no immediate danger exists. Conclusion: the hypothesis of a Pluto-Neptune collision, while intriguing, is not supported by current evidence. Pluto's orbit, though eccentric and inclined, is stabilized by a 3:2 resonance with Neptune, asynchronous oscillation, and the gravitational influence of Jupiter and other planets. These mechanisms have maintained equilibrium for billions of years, making a collision highly unlikely in the foreseeable future. Nevertheless, the discussion underscores the dynamic and ever-evolving nature of our solar system. Pluto's orbit serves as a fascinating case study in celestial mechanics, illustrating the interplay of chaos and stability. Continued observations and computational modeling will enhance our understanding of these processes, shedding light on the broader workings of the cosmos. As we probe deeper into the mysteries of the outer solar system, Pluto remains a symbol of the unknown, reminding us that even in a seemingly orderly universe, surprises and complexities abound. Whether or not a collision ever occurs, the study of Pluto's orbit will continue to inspire curiosity and advance our knowledge of the celestial dance that defines our cosmic neighborhood. Exploring the Pluto-Neptune collision hypothesis, further insights and implications. Revisiting the claims, a closer look at Kaku and Tyson statements. The provocative statements attributed to Michio Kaku and Neil deGrasse Tyson about a potential Pluto-Neptune collision have stirred both public curiosity and scientific debate. While these claims have drawn attention to the complexities of celestial mechanics, They require careful scrutiny to separate speculation from evidence. Neither Kaku nor Tyson has published peer-reviewed research directly supporting an imminent collision, suggesting their remarks may be intended to provoke thought or highlight the chaotic nature of orbital dynamics rather than assert a definitive prediction. To understand their perspective, we must consider the broader context of their work. Both are renowned for making complex scientific concepts accessible, often using dramatic scenarios to engage audiences. The idea of a Pluto-Neptune collision could serve as a teaching tool to illustrate the unpredictability of orbits in chaotic systems. However,